Hello everyone, welcome to my calculus lecture. So in this lecture, we study basic differentiation formulas and also we are going to talk about the relationship between continuity and differentiability. First, we are going to talk about basic differentiation formulas. Okay, so if you remember, right, in my previous lecture, we talked about the derivative of, a function, right, y equals f of x at a particular value, okay? But this time, we are going to replace the particular value by just generic, x. So, we can also talk about derivative f prime of x of the function y equals f of x. So the difference here is that, the previously, like, the derivative of a function at a particular, x value, x equals a. So, we denote it by f prime of a, right? So f prime of a, as you have seen, always gives us a number. But in this case, derivative becomes just another function, okay, for this generic x, right? So f prime of x, right, in the case is given by f prime of x, same thing. So limit h goes to 0, f of x plus h minus f of x all over h. Alternatively, right, we have a second definition. F prime of x can be also given by f prime of x equals limit. In this case, x is already being used, so we are going to use z. So limit z goes to x, f of z minus f of x all over z minus x. And the derivative notation, right, f prime of x can be also denoted by the following notations: dy by dx, okay, df of x by dx, or d by dx f of x. So these notations, I mean, you can use any of those, right, or you can stick to f prime of x. Actually, these notations have their own, like, the advantage, okay, which we will see later on. Uh, and these notations is due to, are these notations, right? This notation, is due to Gottfried Leibniz. So we call it Leibniz notation. Okay, so particularly the derivative f prime of a, right? In other words, f prime of x at x equals a can be also denoted by, dy by dx at x equals a, just like that. Okay, right. Alternatively, also, I didn't write it there, but you can also use this notation here, you know, dy by dx. So, depends on people. You also use this notation here. So, at x equals a. Okay, just something like that. Okay, so here's the theorem. Let C be a constant and f of x and g of x be two differentiable functions. I don't think you have seen this word, differentiable. What it means is simply when we say f of x is differentiable or a differentiable function means that f prime of x exists, okay? Right, so uh, that's another word for the function has a derivative, okay, f prime of x. So we simply call it differentiable, right? So what that means is, if both f of x and g of x have derivatives, okay? So f prime of x and g prime of x. Okay, so in that case, we have the following properties hold. dc by dx, the derivative of constant function with respect to x is 0. I mean, that can be easily understood, right? Because the constant function, if you look at its geometric definition, okay, the constant function is what? Horizontal line. Okay, it is a horizontal line, so its slope is what? 0, right? So that way you can easily see that the derivative of a constant function is always 0. Another way you can see this is what, by just the direct calculation using the definition, right? But it's no need. Okay, next one. Derivative of c times f of x with respect to x. So in that case, actually c can come out of the derivative, so it becomes c times d f of x by dx, derivative of it. So this is same as f prime, okay? And last property, derivative of f of x plus g of x is the same as derivative of f of x plus derivative of g of x. Now, all these properties, okay, it can be, well, the first one can be easily seen from geometric, the viewpoint, but all three of them can be easily shown using the definition of the derivative along with what properties of limits that we studied some time ago, right? So that's a straightforward proof, and I'm not gonna talk about it here, okay? The next important, very important, the formula is something called the power rule, okay? The power rule. Uh, so that's here is what it says. Derivative of x to the power n. Derivative of x to the power n with respect to x is given by n times x to the power n minus 1. Okay, where n is actually a real number. So this actually power rule works for any real number n, okay, any real exponent n. Uh, I proved actually this formula for n is a positive integer case using a binomial expansion. So I'm not going to talk about it here in my lecture here, but if you are curious about it, you can find it in my lecture note. Okay, so whose address can be found at the end of my lecture slide. Okay, so here are the examples. Find the derivative of each of the following functions. Okay, so we have 5 examples. So let me go over each one of them. So I'm gonna move to my notepad. So example number 1, that's y equals 3x to the 5. Okay. So its derivative, so we can use y prime, or it can be also use the dy by dx. I mean, either notation is fine, like I said. Okay. Uh, Although this notation, Leibniz notation, has its own merit, like I mentioned before, but there are you know that'll show up, like in my later lectures. Okay, right. So anyway, so here in this case, we can use right. Uh, so d by dx, all right, 3x to the 5, using uh, the property we saw earlier, right? This constant multiple can be brought outside of the derivative. So that's d by dx, x to the 5. So this is where we can apply the power rule, okay? Actually, we know we defined this derivative of x to the 5, right? At a particular value, if I remember correctly, x equals 1 in my earlier lecture, okay? Uh, By using the power rule, that's going to be 5 comes down, right? 5 comes down, x to the power, the 5 minus 1, okay? So that's going to be 15, 3 times 5, 15 x to the power 4. That's easy, right? That's easy. Okay, so no problem. So next example, that's y equals 8 times x to the power negative 3/4, 3 over 4. So dy by dx, that's going to be d by dx 8 times x to the power negative 3 over 4. So again, this constant multiple can be brought outside of the derivative. So 8 times d by dx x to the power negative 3 over 4. Remember, the power rule applies, okay, for any real exponent. So, negative 3 over 4, the same thing. So, uh, you know, right, x to the power n, right, d by dx, that's the power rule, right, n times x to the n minus 1, right? So that's what we have, right? Okay, that's the power rule. Okay, so negative 3/4 comes down, x to the negative 3/4 minus 1. So that equals 8. So 8 times the 3, the negative 3/4, that's going to be 8 divided 4, that's 2. So 2 times negative 3, negative 6, right? So negative 6x to the power negative 3/4 minus 1, that's going to be negative 7/4, right? Negative 7/4. That's it. So that's the derivative, okay? Right? Next example. So we have this function y equals 2x to the power 4 minus x cubed minus 2x plus 7. So dy by dx, okay, so that's going to be d by dx of 2x to the 4 minus x cubed minus 2x plus 7. Okay, once you get used to applying those, the properties of derivatives, right? Later on you don't have to do this, but this is first time, so I'm showing how those, the properties can be applied, right? To evaluate, a derivative. Okay, so in this case, actually, this is what this polynomial can be considered as sum of those four, the terms, right? Okay, so we can separate them as d by dx 2x to the power 4 plus d by dx negative x cubed plus d by dx negative 2x plus d by dx 7. So you remember the first property, right? This is derivative of constant function, so that becomes 0. Okay, and here the constant multiple can be brought outside of the derivative. Negative 1 can come outside. Negative 2 can be also brought outside of this derivative. So this gives us equals 2 times d by dx x to the power 4 minus d by dx x cubed negative 2 d by dx, all right, x. So each one of them now, you just need to apply the, the power rule. So 2 times derivative of, the x to the power 4 using the power rule, that becomes 4 times x cubed minus, this is going to be 3 times x squared dx by dx. That's actually interesting, right? It looks like, dx divided by dx, which gives us 1, but actually, it coincides with the, I mean, this is not actually, the division, okay? That's just notation for finding derivative of x with respect to x, but, it seems like, that kind of, the thinking, like, dx divided by dx, that happens to coincide with the, the applying the power rule. So using the power rule, that's going to be negative 2. 1 comes down, right? That the power is 1. So 1 comes down, 1 minus 1 equals 0. So x to the power 0 equals 1. So this is it, 2. Okay, so now this equals finally 2 times 4, 8 times x cubed minus 3 times x squared minus 2. Okay, so that's going to be the derivative of this guy. Next example. We have f of x, okay, f of x equals 3x cubed minus 4 all over x squared. So this is something new, okay? This is something new we haven't encountered before. This doesn't seem like, something like we can apply the power law. That's the only thing we know besides like the basic, like, the properties of derivatives, right? So other than that, the only tool we know of is the power law. But this is not something we can apply the power law. Actually, it is, all right? So, all you have to do in this case to, remember this x squared is the common denominator for this guy here, 3x cubed, and also minus negative 4, okay? So we can actually separate them, right? Separate this. So f of x can be written as, in this case, 3x cubed over x squared minus 4 over x squared. Okay? And using, the basic, the properties of exponents, right? Exponents that you learned in algebra, right? So in the case 3x cubed divided by x squared, that's 3 times x minus 4 times, in this case, it's x to the negative 2. So we can actually rewrite this f of x in the form where, to which the power law can be applied to which, the power law can be applied, right? That's exactly it is. So here f prime of x equals, right? We're going to do the same thing. Here this time, I'm not gonna do the, the following that, like doing it by, step by step, like, I did the previous case. That's going to be what? 3 derivative of x using the power law, that's going to be 1. And here, negative 4 times negative, so, the x to negative 2, you can use the power law. Negative 2 comes down, so negative 4 times negative 2, that's plus 8. X to the power negative 2 minus 1, that's negative 3, right? So that's the derivative. Okay? Easy. All right, so I'm out of space, so I'm moving to next page, a new page. Okay, so our last example, example 5. So this is also something new. So we have y equals cube root of x squared minus 3 times cube root of x minus 5. Actually, no problem. If you remember the definition of cube root, right? So, this function y can be also written in the form to which, we can apply the power rule. In fact, the cube root of x squared is what? X squared to the power 1/3, right? Negative 3 x to the power 1/3 minus 5, which equals x to the power 2/3 minus 3 times x to the power 1/3 minus 5. Okie dokie. So, we are ready to find the derivative dy by dx. So 2/3 comes down, x to the power 2/3 minus 1, that's going to be negative 1/3, right? Negative 1/3. And negative 3 times 1/3 comes down. So, that becomes what? 1. So x to the 1/3 minus 1, that's going to be negative 2/3. Okay, negative 2/3, right? Negative 2/3. And negative 5 is what? Constant, so it goes away. So that's the derivative. Okay, so next thing we want to talk about is the relationship between differentiability and continuity. But before we do that, let me go back to my notepad. So, the earlier I mentioned that, uh, the power rule can be proved, right, for, the n is the exponent n is a positive integer case using the binomial expansion formula, okay, which you can find in my lecture note, right? But there is also another way you can see this. Um, so I want to actually talk about it before we move on. So sort of like, this is the proof of the power rule. So what I'm going to do, instead of using binomial expansion, it's actually the same idea, but in my case, instead of proving like what, the derivative of x to the power n for, n positive integer using like a binomial expansion, it's kind of complicated, but, what I'm trying to do is using actually induction, sort of, the inductive way to show you, the how, we can get the power law. So what I mean by, inductive approach is, we find the derivative of x, derivative of, the x squared, x cubed, x to the 4, and then, we just find, the pattern, and so from there, like, we are going to generalize it, okay? Right. So, we want to show, right? We want to show x to the power n prime equals n times x to the n minus 1. Okay? Right. So n equals so n equals 0 case where actually, x to the power 0 equals 1. So, it really doesn't matter, right? So, derivative is 0, okay? Which is the same as like in the case, the 0 times x to the negative 1. So, that becomes 0, okay? Right. So that's a really trivial case, right? Uh, so let's start with n equals 1, n equals 1 case, okay? Right. So derivative of x with respect to x. So derivative of x with respect to x. How do you find it? So that's going to be limit uh, h goes to 0, x plus h minus x all over h. Okay, right. So here x cancels out, so that leaves only h divided by h, that's going to be 1. So this overall limit is going to be 1. So we just showed that dx uh, by dx, that's going to be 1, right? Okay, so let's see, if this follows the pattern, right? Okay, so here what we have is so x to the power 1, right? So 1 comes down, x to the power 1 minus 1, which is x to the power 0 equals 1. Okay, so this follows the pattern here, right? So n equals 2 case, we find the derivative of x squared with respect to x by the definition, that's the limit. You can also use like what the second definition, okay? But here I'm going to stick to the first definition, the original one, x plus h squared minus x squared all over h. Limit h goes to 0. So x plus h squared, if you expand it, we get x squared plus 2 times xh plus h squared minus x squared all over h. So we can cancel x squared out, and then the remaining terms have h in common along with the denominator, right? They all have h in common, so we can divide by h. That leaves us 2x plus h. And when h goes to 0, we get 2x. So derivative of 2x squared, I mean the derivative of x squared with respect to x, that's same as 2x. You see that again, this follows the pattern, right? So, x squared prime looks like what? 2 comes down, x to the power, the exponent is what? Reduced by 1. So, the 2 minus 1, which is x, right? So I'm assuming that actually this is how the people discovered it, whoever did the power rule. So initially, like they didn't try to like prove something. I mean, because you don't even know what to prove, right? But they did this. So for n equals 1, n equals 2, n equals 3, and so on and so forth. And then they tried to see if there is any pattern, and they saw the pattern. So they conjectured, okay? So this is the pattern, and then they conjectured that the derivative of x to the power n would be like something like this, n times x to the power n minus 1. But then that's just your conjecture. You have to prove it. So they did prove it, like using the binomial expansion. Okay. Right. So that's actually how mathematics works. We always trying to see we are always trying to see, a pattern, and then once we see a pattern, we hypothesize it. Okay, we hypothesize it, and then once you have come up with a hypothesis, then you prove it. Okay, or disprove it, or sometimes your hypothesis or conjecture can be wrong. So then you have to disprove it, right? Anyway, let's continue. N equals 3 cases, okay, dx cubed by dx. So that's going to be limit h goes to 0, right? So that's x plus h cubed minus x cubed all over h. So we gotta expand this. That's going to be x cubed plus 3 times x squared h plus 3 times xh squared plus h cubed minus x cubed all over h. So here x cubed negative x cubed cancel each other out, and then the remaining terms have h in common, so we can divide h, right, top and bottom by h. So that's what we have. Okay, so this equals limit h goes to 0, 3x squared plus 3xh plus h squared, right? So when h goes to 0, this guy goes to 0, this guy goes to 0, that leaves us only 3x squared, right? So derivative of x cubed is 3x squared. Again, this follows the pattern, right? Okay, so the x cubed prime, 3 comes down, and then we subtract 1 from the power, which is 2. Okay, right. So you can keep on doing this. For n equals 4, n equals 5. Remember earlier in my earlier lecture we talked about the Pascal's triangle, right? So using Pascal's triangle, you have no problem expanding this polynomial here. Okay, and then you can see that for n equals 4, n equals 5, again, like they follow the same pattern. So you see that, inductively, you can conclude that this power rule works. Okay, right. So this is not really a rigorous proof, but this is the one way you can see why the power rule holds. Okay, right. But more rigorously, you can actually prove it, like I said before, using the binomial expansion formula. Okay, of course, if you want to prove it for n equals a rational number, right, or even a real number, in general cases, it's further work is required, but that's the beyond the scope of this calculus course. Okay, so going back to my lecture slide. So we are going to talk about the relationship between differentiability and continuity. Okay? So here's the heads up. As the title of this slide shows, differentiability implies continuity. In other words, if a function is differentiable, so derivative exists, then the function is also continuous. So the differentiability is a local property. So if a function has derivative differentiable at a point, then the function is also continuous at that point. Okay, but the converse is not necessarily true. The continuity, so a function being continuous at a point, does not necessarily mean that the function is differentiable at that point. So that's what I want to talk about. Okay, so here's the theorem. If f prime of a exists, then f of x is continuous at x equals a, like I mentioned earlier. but the converse need not be true. So continuity at a point does not necessarily mean that the function has a derivative at that point. Okay, so let me first prove the first part. To do so, let me go back to my notepad. Oh, I'm gonna need another page. Okay, so here, let me write down. Okay, so theorem, if f prime of a exists, then f of x is continuous at x equals to a. But the converse need not be true. So here's proof for the first part, okay? Right, so let us calculate this. Limit x goes to a, right? Limit x goes to a, f of x minus f of a. Okay, so that equals limit f of x minus f of a, x approaches a, right? So we are going to divide this by x minus a and multiply by x minus a. Okay, you can divide f of x minus f of a by x minus a, no problem. Why? Because x is approaching closely and closely. X is approaching a, closely and closely, right? Very closely a, but x is never equal to a. So x minus a is never equal to 0. Remember that, right? So we can divide f of x minus f of a by x minus a. So if you divide to retain the inequality, right? So this is give and take. So you divide by x minus a, you have to multiply by x minus a. Okay? Now, the first one, okay, so limit of the first guy here is nothing other than f prime of a. And then limit of x minus a also does exist as 0, right? So in that case, using the limit property, this can be written as what? The first, so you can actually, this is what? The product of the limit of this and the limit of this, right? Which gives us f prime of a for the first part, and limit of this second part is 0. Okay, so f prime of a does exist, right? That's the condition, which means that's a number. Number times 0, that's going to be 0, so equals 0. So we just showed that limit of f of x minus f of a when x goes to a equals 0. What that means, what that implies is limit of limit x goes to a, f of x equals f of a. What does it look like? This is the condition for f of x to be continuous at x equals a. Exactly. Therefore, we just showed that f of x is continuous at x equals a. Done. Okay, so no big deal, right? The proof is easy. Now we need to show that the converse need not be true. So it could be true, but it doesn't have to be, right? So certain cases it may be true, certain cases it isn't. So how do we show something like this? Well, in this case, you just need to show one counter example for the converse, right? So you just need to show one example that the converse doesn't work, right? Doesn't work. So that's called the counter example. So here's a counter example. Example for the converse. So my counter example in this case is, the f of x equals the absolute value of x. Okay, the absolute value of x. Well, you see the graph of the absolute value of x, right? Let me try to draw. So in this case, I'm going to draw to axis. Okay, so that's x-axis, y-axis as 0, and the graph is going to be going like that, right? So okay, so in fact, this part here is a graph of y equals x, and this part is a graph of y equals negative x. By definition, right? Definition of the absolute value. So when x is negative value, it's defined by negative x. Remember that, right? Okay. So from of course it is continuous. From the picture you can easily see. Okay. But particularly, I mean, it is continuous at x equals 0. So you can see that from the graph, or you can use the definition. If you take the limit of absolute value of x when x approaches 0, right? So the right hand limit, left hand limit both equal to 0. Okay, so that's same as f of 0, right? F of 0. So let me write it down. What I just said is limit of absolute value of x when x approaches 0. That's same as 0, which is f of 0. Okay, so it is continuous. So but actually absolute value of x is continuous everywhere. This is continuous at x equals 0. But it is not continuous. No, but it is not differentiable at x equals 0. How do we know? Well, look at the picture. So from the picture, you can easily see. So from the right side, right? That's the graph is the y equals x. So slope of tangent line. So usually when we say like a tangent line is what? A line which is tangent to a curve, right? Tangent means that it is touching the curve at a point in general, right? But there is an exception. If your curve is actually a straight line, the tangent line is actually itself, all right? So there's no touching at a point, but they have to overlap, right? So y equals x itself is also tangent line, so slope is 1. From left side, you see that slope has to be negative 1. So they are not the same, right? But let's confirm this by calculation, okay? So here, what is supposedly like f prime of 0 is going to be limit h goes to 0, right? H goes to 0, f of x plus f of 0 plus h minus f of 0 all over h. So that equals limit h goes to 0, f of 0 plus h is f of h, which is the absolute value of h. And then f of 0 equals 0. Also, I don't need actually this long line divided by h. Okay? Since this involves absolute value, we need to separate this limit to the right-hand limit and left-hand limit. Okay? So let's calculate left-hand limit first. So the limit h goes to 0 from the left side, right? From the left. So left-hand limit case. Since h is less than 0, absolute value of h is going to be negative h, okay, divided by h. So h is cancels out, that leaves us negative 1. On the other hand, limit h goes to 0 from the right, okay, so right-hand limit absolute value of h is just h, so h divided by h, that gives us 1. So left-hand limit, right-hand limit at x equals 0, they do not coincide. The left-hand limit is negative 1, right-hand limit is 1, as we observed from the graph of the absolute value of x, right? Okay, so in that case, since the left-hand limit and the right-hand limit do not coincide, what is that? This does not, f prime of 0 does not exist. So we see that this example tells us, right, that the continuity of a function at a point does not necessarily guarantee the existence of the derivative at that point. Okay, so going back to our slide, I believe this is the end of my lecture today. I mentioned about the common example here, right? Okay. Right. So, the more details of my discussion in this lecture can be found in my lecture note. Lecture notes at the following two addresses. Okay. Right. Again, both addresses are hyperlinked, so all you have to do is to click on each of them to get to the page. And also, as usual, if you want to get to my main blogger site where you can find the other lecture notes, you simply click on this word blogger, which is also hyperlinked. Okay, thank you very much for listening and watching my lecture. I'll see you next time. Thank you. Bye bye.